Hey everyone, let's go over empirical and molecular formulas. So we're going to be on this page of your packet. So first off, an empirical formula is going to be the simplest whole number ratio. Oopsie. Number ratio of atoms in a molecule. So you can look at your subscripts. If the subscripts can be divided by the same number, that is not an empirical formula, okay? So while the empirical formula is the lowest ratio, a molecular formula is going to tell us the actual number of atoms in a compound or molecule. So something that biology talks a lot about is glucose, which is C6H12O6. And this, you can see all of these subscripts, 6, 12, 6, they can all be divided by the same number. This is a molecular formula because it's telling us how many carbons, how many hydrogens, how many oxygens are present in glucose. But that's going to be your molecular formula. The empirical formula of this would be then CH2O, because that's what it is after you take your lowest whole number ratio. So some empirical formulas can be the molecular formula. If you look at water, for example, H2O, that is the lowest whole number ratio because you can't divide the subscripts by the same number. And it's also the molecular formula of water because that's what water is. It's 2 hydrogens for every 1 oxygen. If you look at hydrogen peroxide, which is H2O2, would that be an empirical or a molecular formula or both? This would just be a molecular formula because both of these subscripts can be divisible by 2. So the empirical formula would be HO. Okay? So we can actually use data to calculate the empirical formulas. Okay? It's a little step here. And there's a little saying that we use to help us to remember what our steps are, and it's poor grades. You can write this wherever. Oops. Poor grades make dad mad. Because with our steps, what we're going to do is we're going to go from percent to grams, and then we're going to go from grams to moles, and then we're going to divide by small and multiply to get whole. Okay, so those are the steps: percent to grams, grams to moles, divide by small, multiply to get whole. So poor grades make dad mad. All right, so when we're doing our calculations, the first thing that we're going to do is go from percent to grams. So we would assume that we have a 100 gram substance and just change our percent sign to grams. So we would say that we have 79.3 grams of carbon, and we would have 20.2 grams of hydrogen. And we're trying to find the empirical formula. So then the next step would be to go from grams to moles. And we already know how to do that because we would take the molar mass, use that to convert between grams and moles. So we would divide by the molar mass for each of our substances. 20.2 grams of hydrogen. We're going to put 1.01 grams of hydrogen down here. 1 mole of hydrogen up here. Okay, so we would have 79.3 divided by 12.01, and oops, I did multiply. We're not going to worry about sig figs here yet. If you round too early, you're going to mess up your answer and make it more difficult for you later on. So don't round to sig figs too early. So 6.60283. You don't have to write all of the numbers. And then we would have 20.2 divided by 1.01. And that's actually just 20. Now we want to make sure we remember this is moles of carbon and this is moles of hydrogen. So then our next step is going to be divide by small. okay? So you take your moles here. So we had, excuse me, 6.60283 moles of carbon, and we had 20 moles of hydrogen. And you divide both of these by the smallest value. So we're going to divide both of these by 6.60283. So this is obviously going to be 1 mole of carbon up here. And then down here we have 20 divided by the 6.60283. And we would get 3.029 moles of hydrogen. So then step 4 is multiply to get whole. So that means if you don't have a whole number, so when you do that dividing by and you don't have whole numbers, you're going to multiply these by the same number to get them into a whole number. Well, these are both close enough to a whole number, 3.029, that's basically 3. Okay, so we're not going to be concerning ourselves with multiplying to get a whole number here. So then we just have to write our formula. So that means that we have 1 carbon and we have 3 hydrogens. Oops, wrote the wrong number. 3 hydrogens. Okay, that's our empirical formula. Now, let's say that we had a compound and we had a molar mass. Oopsie. Let me just clear this out. Let's say that I had an unknown substance and it had a molecular formula of about 30 grams. And we know that the empirical formula was CH3. And I asked, well, what would that molecular formula be? So what you would do is you would take the mass of the molecule, which is 30, and we're going to divide it by the molar mass of the empirical. So we would take 12.01 plus 1.01 times 3, because there's 3 hydrogens, and that's 15.04. So when we do that, we can see that we would get, I multiply by, again, must be getting tired. We would get 1.99468, blah, blah, something else, okay? So that's basically 2. So that means that our molecular formula is 2 times our empirical formula. And so our molecular formula would actually be written then as C2H6, indicating that it's 2 times as large as our empirical formula, okay? So if you have to find the molecular formula, you would take the mass of the molecule divided by the molar mass of the empirical formula, and then whatever ratio that is, you would multiply each subscript by that to write your molecular formula. So let's take a look at this other example then. So here we already are in grams. We have the grams of each of our substances. So we don't have to do the percent to grams. We can just do grams to moles. So we have 4.151 grams of aluminum, and we have 3.692 grams of oxygen. So we can multiply these by our conversion factors to get rid of the grams and end up with the moles. So we put the molar mass of each thing on the bottom. Down here, we're going to have the molar mass of oxygen on the bottom, the molar mass of the 1 mole of oxygen at the top here. So we'll take 4.151 divided by 26.98, and that gets us 0.153855. Again, you don't have to write all the numbers, but don't round yet. Moles of aluminum. We got a 3.692 divided by 16 to get us 0.23075 moles of oxygen. So let me move this down, scroll this down. So we're going to divide by small. So we have, again, 0.153855. moles of aluminum, and we have 0.23075 moles of oxygen. So we're going to divide both of these by small, which means we're going to divide both of these by that 0.153855 number. So we're going to get 1 mole of aluminum. We're going to divide this by 0.153855, and we're going to get 1.5 moles of oxygen. So we know that we can't have half of an atom in a formula. We can't have like 1 aluminum and 1.5 oxygens. So we have to multiply these values to get a whole number for the oxygen. So what you're going to want to do is you're going to want to look at what's after the decimal and ask yourself, what do I have to multiply to get rid of that decimal or that fraction? So if I have 1.5, I'm going to have to multiply this by 2 in order to get rid of that. But you can't just multiply the 1.5 by 2 to get 3 moles of oxygen. You have to multiply both things in order to get that correct ratio of aluminum to oxygen. So this is telling us that for every 2 moles of aluminum, we would have 3 moles of oxygen. So our formula then would be Al2O3. Okay? So give those empirical molecular formulas a try in your packet and let me know if you guys have any questions on how to do these things. And good luck.